Okay, good morning everyone. That was an ideal introduction to my presentation because several of the things that I'm going to mention Alak has already covered and it helps me put in context. This is a collaborative paper between the group at Department of Primary Industry Victoria and the University of Melbourne, Department of Geomatics and CRC for Spatial Information. Alak mentioned work in representation of climate change, and that's the case study I'm going to show you here. And I'm going to kind of, once again, as Chris has done at the beginning, rationalise the reason we use visualisation, talk about the structure we've put together to deal with climate change, talk about some aspects of the modelling that was underlying that was done through Monash University and DPI, and then specifically the visualisation aspects. I should say at the beginning that the focus in the work we've been doing is in real-time visualisation and creation of collaborative virtual environments. So our focus has not been on high-quality photorealistic representation. It's been on taking a game engine, building on that, and looking at what kinds of interactive decision support processes we could put in place. In this particular instance, we're not using most of those, but the technology I'm showing here was developed with that in mind. So why do we want to visualise climate change? Well, we know that certain extremes, increased cyclone rates, droughts, etc., are easily recognisable, but it could be that, you know, small changes that are progressive and not so easily recognisable. You know, do we know exactly what 2 degrees C a year means in terms of the long-term effects? These changes tend to be less than the year-to-year averages, but there's still a scope. Well, and that means that often people on the land making decisions about land management are reacting to year-to-year changes rather than to the long-term trend changes. However, it may be important for them to also know the long-term trend changes and be able to think ahead and adapt to and plan for with those. So the land manager needs to understand that change in climate. The land will respond to the change in climate and the way that a range of options will perform given those changes. And so our work was to do with creating the tools that can help to provide that understanding, and also to deliberate and think about and communicate with others about the possible responses to those changes. This is the broad structure of what we've been doing, and I'll talk about little sections of this in turn. So I'll start with climate models. As I mentioned, these were basically, the starting point here was the IPCC global climate models. The colleagues at Monash developed systems for regionalisation of those down to 5-kilometre grids, and this first stage then worked, and that was done incorporating local biophysical data from the GIS. So, yeah, the base level CSIRO climate change model was taken down to its 5-kilometre grid, as I've already mentioned, and that local variation as modelled can then be input into land suitability and other kinds of impact models at the local scale. And this is an example of one of those change maps. This is in southwest Victoria, the same area that Alak has introduced to you, and shows the probable changes in temperature. I think it's the difference between current and 2050. So having got that mapped, we can then think about how that mapping translates into land suitability. And And this is mainly the work of Victor Esposito from Department of Primary Industry. And it relates to the ability of the land to support particular agricultural commodities. And Victor, I think, did 4 or 5 or 6 different things from barley to blue gums in his analysis. And that analysis used expert input through analytical hierarchy and other multidimensional weighted approaches to what are the key input factors, and the output was ArcGIS maps. And ArcGIS maps, and one of those for each agricultural commodity. And those GIS maps, like this is the ryegrass land suitability under a particular global scenario, regionalised using the 5 square kilometre grids, and then turned through these weighted multifactorial analysis into a probable growth range. Okay, so now the next stage was to visualise what that really means in the landscape and to think about how that visualisation could be effectively used. And so again, we went back to the base GIS data. We used some technology that we've been developing, a suite of products that we call SIV, Spatial Information Exploration and Visualisation Environment. SIV Builder is a tool for taking GIS data anywhere you can zoom into and automatically building a base environment for that area. SIV Direct allows live interaction with ArcMap so that you can change the scenarios on the fly by selecting polygons and saying, I want that polygon filled with a certain species of trees or an ecological vegetation class or a crop or a set of grazing animals or whatever. And SIV Viewer is the game engine derived product for viewing all of that. So in that southwestern area, slightly different farm from the one that Alec described, but in the same general area, we selected a small area of land, built 2 hypothetical farms with the surrounding paddocks, and said, well, these are going to support a range of activities such as sheep, wheat, blue gums, and also the use of biozones as a landscape remediation measure. Okay, fortunately you can read that. So SIV Builder works fairly simply by taking the kinds of 3D models that Alec has described as belonging in an object library, feeding those through with the land use changes into the GIS and coming out with the virtual world. So having got that base virtual environment, what's the next step? The next step is to say, well, precisely what are we going to put into different parts of that reflect those changes in land suitability and also reflect the changes in management that could occur in order to counter the changes in land suitability. So that's done by this process we call SIV Direct, where you see here the little interface that pops up in ArcMap, and there's a selected polygon just here, and that polygon we select fill with blue gum plantation, for example, and that fills over here. And there are different blue gum models representing different ages of growth, and we can specify also the height, and that draws on the appropriate model within the system. There's also the scope there for combinations of species that make up ecological classes. And so back here is a biozone, and here you can see some sheep in paddock and so forth that have all been put in there through this interactive scenario building process. What we did then was say, okay, well, let's consider we've got one farm that is responsive to change, thinks about what they're doing, adapts